Okay, so we're going to continue talking about intermolecular forces and how to tell which substance is stronger or weaker. And then in follow-up to that question, then who has the higher boiling point, the lower boiling point, et cetera, all kinds of different questions that can follow from that. So we already know that I hate dirty laundry, that ionic is the strongest of the bonds. And then we have all the way down to ionic, then we have hydrogen bonding, then we have dipole-dipole, where we have the actual pole, dipole, and it's polar, and then we have London dispersion, where we have non-polar, very weak molecules, intermolecular forces, therefore really low boiling points and melting points. So what if we have multiples, though, of these types? So say you have ionic, but there's 2 of them, or 3 of them, or however many. The process goes like this. For ionic, there's actually 2 rules. If it is the stronger of the 2, will be the larger charge product, and that's the absolute value of that. What do I mean by charge product? I mean, what is the charges, and then we take the product or multiply them together. So let's look at this example. We have magnesium chloride, or we have aluminum oxide. Both of them being ionic because we have a metal, magnesium first, and we have aluminum, the metal, first here in this one. So they're both ionic. So now we know they're stronger, but which one is stronger of the 2? So let's look at the product charge. So again, we look up our charges. We know magnesium is a +2. A +2. But again, we're going to take the absolute value once we multiply them. Chlorine is a -1. Now notice I'm only going to take a -1 for the chlorine. Even though there's 2 of them, it doesn't matter how many of the atoms we have, it's still just that atom's charge. So +2 and a -2, absolute value will multiply to give you 2. Whoops, showed my work there. I wasn't being very clever. So we have a product charge of 2 for magnesium chloride. Now going on to aluminum oxide, aluminum has a charge of +3, correct? And that doesn't matter whether there's 2 or more, we're just going to have +3. Oxygen's going to be a -2. Again, ignoring that there's 3 of them, it does not matter. So 3 times 2 is 6. So if we now look at it, we're going to say, okay, well, 6 is much larger than 2. It doesn't even have to be much larger, it just has to be larger. So because it has the larger product charge, that makes it the stronger of the 2. So because it's got the biggest product of charges, it'll be stronger than the magnesium chloride. That means it'll have a little higher melting point, a little higher boiling point. We'll stay together a little longer. It is stronger. Now, what if that doesn't work? So we are going to have another second rule here. And it says that if this is going to be stronger, you're going to have the atoms that are closer together. So the smaller the separation between the ions, or the smaller ion separation, makes them stronger. So smaller is stronger in ionic. So that means if I'm going to compare 2 ionic substances yet again here, I'm going to compare magnesium oxide and strontium oxide. Now I've chose these because hopefully it'll be a little bit easier. Magnesium is a metal, so is strontium, so they are both ionic, but who is stronger? If you look at the actual substances, they share oxygen. So basically all we have to do is compare the magnesium and the strontium, and we'll figure it out. If you look at a periodic table, remember who's the largest atom of them all? It's francium. So going toward francium, we get larger. So who's closer to francium? Well, that would be strontium. So strontium, well, real quickly, sorry, I should have said that first. Sorry, go back real quickly. If we had done the product charge, you notice both of them are 4. That's why we had to move on. I'm sorry. So I should have done the product charge first, which I did in the first example, but now I should have shown you that it didn't work in this case. That's why we had to go to the radius, or the smaller ion separation. So as I was saying, strontium is larger, and due to its larger radius, that means they are farther apart. When they are farther apart, strontium larger, so they're farther apart than magnesium, therefore they are weaker. If you're trying to hold on to somebody and your arms are reaching out farther, that means you're going to have a harder time than somebody very, very close, like magnesium oxide. It's going to be much closer and stronger because they are close together, holding on very, very tight, smaller distance between them. All right. Let's move on. So that is ionic. Now, ionic, you have to have its own category. Each type of intermolecular force does. So now we're going to move on to what if there are multiple dipoles? If there's multiple dipoles, so there are polar molecules, you're going to go by the more different in electronegativity. So the bigger the electronegativity difference, the more polar. So the more they pull, the more polar they are. All right. So let's look at an example of two polar molecules. We have HF and HI. They both have the hydrogen, again, to make this a little easier to see and very clear to begin with. I could write down the electronegativities. I could also tell from how far away they are, kind of on the periodic table, but we'll go ahead and use electronegativities. You can see that for hydrogen, it is going to be a 2.1. Now, you could look these up on a table, or we would give them to you if we expected you to do this. Fluorine is a 4.0. We all know it's the highest electronegativity. So if you want to take the difference in electronegativities, 4.0 minus the 2.9, whoops, I'm not going to give you answers, is 1.9. Now, on the other hand, if you look over at HI, we have 2.1 for the hydrogen, 2.6 for the iodine. Subtracting 2.6 minus 2.4 only gives me 0.4 difference. So, of course, as you can see, it's already hinted at here. The HF has more difference, a larger electronegativity difference. Therefore, it is more polar. So the more different, the more polar, the stronger. So more pole means stronger, larger electronegativity difference means stronger. So polarity just has to do with how different they are. The more pole, the stronger, the more different, the more polar, the stronger they are. So that's dipoles. What about if you have multiple London dispersions? Now, you actually have to understand London dispersion a little bit before we can really go to here. London dispersion, what it is a disturbance in the force. So it's like have you ever had your washing machine or your dryer kind of go off balance? And dunk, 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 okay, all of a sudden it's got an absolute, something went out of balance, but you can go and fix it very quickly. Well, in a London dispersion in an atom, that's what happens. It actually, all of a sudden it gets pulled a little, but then it goes right back. It's only temporary. It's a very quick little distortion is what we're going to call it, or disturbance. So London dispersion is based on that dispersion. The larger the distortion, the larger or the stronger that London dispersion, even though they're all weak. So writing that down very quickly, the larger the atom or the molecule, the stronger the dipole force, because there's more to distort. So again, if you have a bigger atom, you have a lot more out there that can be distorted or moved around compared to a small little atom who doesn't have much to distort. So more distortable, like I said, okay? Which would be more distortable or stronger of the London? Remember, again, strong of the weak. Who will it be? Well, I kind of had the arrow already pointing it to it, but neon or xenon. Neon and xenon are both noble gases, so they're both London dispersion. As you go down a column, xenon gets larger, neon is quite a bit smaller. And since xenon is larger, it is more distortable, and larger means stronger London dispersion. Again, strong of the weak. So in comparison, your xenon would be the stronger of the two since it is larger.